Greetings, everybody. Welcome to the latest edition of the Physics Corner. I'm your host, Dr. Christopher Sorolla, and this is a series of videos in which we show how to set up and solve simple physics problems. Today's problem involves resistance, specifically resistance of a wire. So, what we're interested in knowing to calculate the resistance of a wire are three things. One, we need to know what material the wire consists of. We also need to know the thickness of the wire, and we need to know the length of the wire. So let's imagine the following scenario. Suppose you are a technician, perhaps, or just you'd like to throw parties, and you're setting up to have music at a concert. You need to have 60 feet of wire to connect the power supply to your speakers. What kind of wire should you choose? Now, almost inevitably, you're going to end up with copper wire, simply because that is the most available wire. That is not cheap wire, but it's cheaper than most other options. That is what manufacturers are going to give you. You'll probably also have stranded wire versus solid wire for flexibility. We don't need to worry about the stranded versus solid for our purposes here, turns out, but I thought I may mention that. The other thing that comes of interest specifically for wire is that there's a system in the United States, at least, called the American Wire Gauge. That represents thickness of wire. Now, unfortunately, it's not a simple system necessarily, but fortunately, you can look up the numbers, and we've done that here. So let's suppose that in storage you have either a choice of what's called 14 gauge wire or 18 gauge wire. Now, it turns out that 14 gauge wire has a thickness of 2.08 square millimeters. In other words, that's the cross-sectional area. So if we're to look at, say, a picture of a section of the wire right here, that is the cross-sectional area, we'll call that capital A, of our wire. Now, the length we're going to be interested in would be something like this. And again, I'm just showing a section for illustration purposes, but that's the idea. And the copper is something else, which we will talk about in a moment. Notice something different or interesting about the 18 gauge wire. 18 gauge, you might think automatically that must be thicker wire. It works backwards. 18 gauge wire is actually thinner wire, 0.823 square millimeters. All right. Or again, that is a cross-sectional area. And we're going to have to calculate or change units from square millimeters to square meters, but of course we'll show that as we go along. One more thing as additives before we get here. Rho is the density of the copper wire. It's copper we're going to use, so Cu is the elemental symbol for copper, of course. The number is 1.68 times 10 to the negative 8th ohm meters. Notice, by the way, it's ohm meters, not ohms per meter. Okay, it's easy to get that confused or to think that a lot of times in a lot of quantities we use it's something per something else. In this particular case, that's ohm meters. This particular idea of the rho here, it's not a density, rather it is something called resistivity. It is the resistance, if you will, of a material against electrical conductivity, and that is given in terms of ohms multiplied by the number of meters that you go. Okay, so if you want to calculate the actual resistance, which is what you need if you're going to talk about, say, the power that you need to supply to the speakers, or the loss of power more specifically you might be concerned with, the formula for that is R equals rho L over A. Rho, again, is not density, it's resistivity. Capital L is the length, capital A is cross-sectional area. So this is your general formula. And what we want to know here, or at least a start of a discussion here, is which wire would make the most sense if you have your druthers. Now again, of course, there's other options, right? If you only have one wire, that's the problem. If you have some kind of cost issue, that's another problem. But we're going to assume that cost is not the problem. Both kinds of wire are available for your use, and you have enough of each wire, so it's merely just comparing the total resistance of each wire that's going to matter. So along the way, let's go ahead and calculate the resistance. Now, I will say also, just to say it, we're not going to calculate here in this episode the amount of power loss you'll have. That would depend on the current that you're applying to the system, and we're not talking about that for today. So in any case, the resistance from the 14 gauge wire, I'll write it like that, would be equal to the density of the copper, because that's the kind of wire we're using, the length, and then divided by the cross-sectional area of the 14 gauge wire. So I could take this general formula and make it a little bit more specific to our circumstance. All right, so 1.68 multiplied by 10 to the minus 8th ohm meters. To save us a little bit of time, I've converted 60 feet into meters and give us a little bit of extra significant figures there just to do that for our purposes of calculation. Area here is 2.08 millimeters squared. And I need to convert that into meters. How would I do that? Well, there's 1,000 millimeters per meter, right? So I would write 1 meter per 1,000 millimeters. Notice the way I'm doing this, I've got millimeters squared here. I want to cancel the millimeters here, and also I need to square this. 1 squared is not going to matter, but the 1,000 squared, that will make a big difference. Okay, so let's take a look at units just to make sure we're going to get what we need. Meters times meters squared here, divided by meters squared here, so those will cancel. Millimeters squared divided by millimeters squared in the denominator also cancels, and we will be left with ohms. All right, so take a moment to go ahead and calculate this. When you do, you get 0.148 ohms. Not a lot of resistance. Okay. Now, we're also talking about a system where we are using we're only talking about the resistance of the wire. It's a little bit more complicated than we're letting on here because what we're calculating is just, say, the DC or direct current component of the equivalent of resistance. You will find out later on, if you go on to study AC circuits, that we would need to also incorporate other facts. We'd also need to know, for example, the frequency of the alternating current, for example, some other things too. We're not worried about that. We're only worried about the contribution of the straight up resistance of the wire, not anything else, just for simplicity's sake. What about the 18 gauge wire? How does it compare? Well, same calculation, except now we're dividing by the area of the 18 gauge wire. So the top will be the same set of numbers, right? Well, that won't be any different. But now the bottom, or denominator, will be 0.823. And again, that's in square millimeters. And so again, we need to make that conversion from millimeters to meters, or square millimeters to square meters. When we do this, the resistance of the 18 gauge is 0.373 ohms. Now, that doesn't seem like a lot either, but notice what's happened. It's more than double the amount of resistance that we got from the 14 gauge. And again, we are simplifying this a little bit. We're not concerned with the alternating current, say, properties or effects that it would have in this case. But this would matter. You have basically more than twice as much power loss with the 18 gauge that you do with the 14 gauge. So other things being equal, and again, they're not always are equal in everyday life, but other things being equal, it's going to be better to have a thicker gauge wire. It's going to have, because there'll be less resistance. That's something that's kind of interesting. If you look at our formula for resistance, it depends on the resistivity, which is a material idea, depends on the length, and it makes sense. The longer the wire is, the more resistance you'll have, but it's inverse compared to the cross-sectional area. Here's a way to think of that. If you are, say, as a different analogy, suppose you have a crowded classroom and class is done, bell rings, instructor's done or whatever, and it's time to leave. If you have all the students trying to go through one narrow door opening to get out, it'll take everybody a while to file out of the classroom. But imagine there's a really wide door, or like a kind of garage, or there's even multiple doors. People will be able to get out faster, right? And that's what the idea is here. The more narrow the opening, the larger the resistance. The wider the opening, so to speak, the less the resistance. And that's what we see in this calculation. All right, so food for thought in case you ever throw a party. Thank you very much for your attention. Our funding comes from the University of Mississippi and University of Southern Mississippi. Technical support from Sidney Gautrow and Sophia Turner. I am again your host, Dr. Christopher Sorolla. Thank you for your attention, and clear skies.